Hello again. We've learned how to calculate the derivatives of many different types of functions, and we've now also learned how to calculate derivatives of implicit functions. So now we're going to look at a couple other special cases, inverse and hyperbolic functions, and how we can calculate the derivatives of those types of functions. We're going to start with inverse functions, and to get there we have to develop a technique. But if f and g are inverse functions, then it turns out that g prime at x is equal to 1 over f prime at g of x, where again f and g are inverse functions. Now this isn't too difficult to prove. What we need is to recall something that's true about inverse functions. So recall that if f and g are inverse functions, we know that f of g of x is equal to x. That's probably the most important property of inverse functions, is that, in a sense, they undo each other, right? So as a quick example, recall, let's let f of x equal x cubed and g of x equal the cube root of x. These are inverse functions. Then f of g of x would be the cube root of x cubed, which is x. Okay, so that was just a quick example, quick reminder of that. Let's go back over here. We're trying to prove this statement I said earlier, that if f and g are inverse functions, then g prime of x is the reciprocal of 1 over f prime at g of x. Alright, so if f and g are inverse functions, then f of g of x is x. Let's differentiate both sides of this equation with respect to x. So then d by dx of f of g of x is then equal to d by dx of x. On the left-hand side, what do we need to do here? Think about that for a moment. On the left-hand side, we must apply a chain rule. The right-hand side is relatively easy. D by dx of x is just 1. But now on the left-hand side, if we were to apply the chain rule, we would have f prime at g of x times g prime at x. And that's just straightforward chain rule that we learned. That's the basic concept of it, really. So then g prime of x is equal to 1 over f prime at g of x. Just to use a little bit of division there. And so we've proven this rule for inverse functions, is that if we know we have inverse functions, then we can calculate the derivative of one of those functions by using this interesting notation. So let's see an example of that. Earlier in the course, I told you that d by dx, the derivative with respect to x of natural log x, was 1 over x, but I couldn't prove it to you because I didn't have this technique yet. So now let's prove that statement. So let's call the g of x equal to natural log x, because that's what we're trying to find the derivative of. Well, the inverse of natural log x, that you learned in algebra, then let's let f of x be its inverse, which is e to the x. And we know that f of g of x would be e to the natural log of x, which is x. They are inverses. Alright, so we're calling g of x natural log x, and f of x is e to the x. We also know that the derivative of the f of x, right? We know that f prime of x is also e to the x. All right, so now then d by dx of natural log x. Remember, that was my g of x, right? That was my g of x. This would then be equal to 1 over f prime. F prime was e to a power. E to a power. F prime at g of x. At natural log x. Well, we know that e to the natural log x is 1. I'm sorry, e to the natural log x is x. So we end up with 1 over x, which is what we stated earlier in the course. The derivative with respect to x of natural log x is 1 over x. So, d by dx of natural log x is in fact equal to 1 over x. Now, we're going to use this same sort of technique to develop derivative formulas for some other inverse functions, the inverse trigonometric functions. So you learned about these inverse trigonometric functions back in your trigonometry class, or at least I certainly hope you did. If not, that might be something that you want to review. So for example, let's say we wanted to find the derivative with respect to x, d by dx, of the sine inverse function. Again, I will think of this as my g of x. All right, so I'm going to let g of x equal sine inverse x. Then f of x is equal to the sine x function. But now remember, hopefully you remember, that when you studied these back in your trigonometry class, we had to put restrictions on the sine function to create the inverse function. So recall that this sine function was only valid, right? To create the inverse, we had to restrict the sine function so that it was only defined on negative pi over 2 to pi over 2. And then the y values for this function were between negative 1 and 1. And so then for this inverse function, we invert the domain and range. And so for the sine inverse function, it's only valid where x is between negative 1 and 1, and its outputs are between negative pi over 2 and pi over 2. We also know that for f of x, we know that its derivative, f prime of x, is cosine x. So now let's see how we can use this. Alright, so then d by dx of sine inverse x, using that formula we saw on the previous slide, that would be 1 over cosine, let's use similar notation here, cosine of arcsine, sine inverse of x. Now, we have to do something with this. We can't just leave it like this. It's not a nice notation. Cosine of sine inverse of x. Turns out, though, that we can manipulate this. We can think of this. Alright, so sine inverse x means that we have some y value between negative pi over 2 and pi over 2. And we tend to think of that as an angle. So let's draw this. Alright, so if we draw an angle, a y value, between negative pi over 2 and pi over 2, and think of that as an angle. Alright, so here's one possibility. If we had this one, let me call this my y1. There's my y1. It's some angle. And I can build a reference triangle where the sine is equal to x. So the sine of y is equal to x. So the sine of y, we tend to think of that as an opposite over a hypotenuse. The sine of y is equal to x. So thinking of that as an x over 1, opposite over hypotenuse. And that's if x was positive. What if x was negative? So here x is positive. What if x was negative? If x was negative, then we would have this reference triangle, where here's maybe my y2. And here's where x is now a negative. And again, the hypotenuse is 1. Now, in either case, we want to be able to calculate the cosine of that angle y. So now I have to evaluate the cosine of this angle y. All right, so to evaluate the cosine, thinking back to trigonometry, we tend to think of that as the adjacent over the hypotenuse, which means I need this measure right here. I need this measure of that adjacent leg. So we use a little bit of right triangle information. We apply the Pythagorean theorem, and it turns out that this leg that I marked in yellow is equal to the square root of 1 minus x squared. That's just from the Pythagorean theorem. And so then d by dx of sine inverse x is equal to 1 over the square root of 1 minus x squared. And so there's the derivative of the sine inverse function. And remember, I could have also used the notation d by dx of arcsine x. That's an equivalent notation. All right, so now that you've got this one, now that you've seen this example, can you use this example to try and find d by dx of cosine inverse of x? Now would be a good time to pause and see if you can do this one on your own. So using a similar format, similar idea, I'm going to call the cosine inverse, I'm going to call that my g of x. So I'm going to let my g of x be cosine inverse x, and then I'll take the f of x to be the cosine function. But again, it's a restricted cosine function. And here, recall when we developed the cosine inverse function, we let the cosine function only be valid from 0 to pi. And that gave us our entire range for the cosine function from -1 to 1. And we know that if f of x is cosine x, then the derivative of the cosine function is negative sine of x. Right? And then going back to the g of x here, if f of x is only defined on 0 to pi, where the y value is between -1 and 1, for the inverse function, we invert those. So the cosine inverse function takes the x values from -1 to 1 and outputs values from 0 to pi. All right, so now d by dx of cosine inverse x is 1 over negative, let me again be careful with my notation here, trying to be consistent, 1 over negative sine of cosine inverse x. And we tend to think of that as a negative sine of some y value. Now here, because we're using the cosine, it's a little different. Our drawing is a bit different than when we were developing for the sine. Now, since our angle, our y, is between 0 and pi, we could have a first quadrant y value, right? So let's call this my y1. And there's my reference triangle. And here, since it's a cosine, we tend to think of cosine as adjacent over hypotenuse. So we have cosine of the y is x over 1. Cosine of the angle is adjacent over hypotenuse. So here's x positive over 1. Or if we had the y values between pi over 2 and pi, that would mean we would have a quadrant 2 reference triangle. And here, this would be the angle, this would be the y2, where again we would have adjacent over hypotenuse. And so here would be the x negative. Now in either case, we need to calculate the sine of that angle y, right? We need the sine of y. And so to calculate the sine, we need the opposite side. We need to find this leg of each of these triangles. And again, if we apply the Pythagorean theorem, this leg ends up being the square root of 1 minus x squared on either side. Square root of 1 minus x squared. Because it doesn't matter if x is positive or negative, once you square it, now it's positive. So the square root of 1 minus x squared has to be positive. And if we look at the drawings, that square root of 1 minus x squared is above the x-axis. It must have a positive coordinate in that sense. Alright, so then the sine of cosine inverse x, the sine would be opposite over hypotenuse. And so we'd have the square root of 1 minus x squared over 1, or the square root of 1 minus x squared over 1. And so this ends up being 1 over negative square root of 1 minus x squared. And so what we normally write is that d by dx of cosine inverse x, which is equivalent to writing d by dx of the arccosine of x, is negative 1 over the square root of 1 minus x squared. So there's the derivative formulas for the arcsine and the arccosine. Why don't you try this one out? See if you can find the derivative of the arctangent function by using a similar method. Like I've done before, I'm going to call this function on the inside that we're trying to calculate the derivative of. Let me call that the g of x. So I'm going to let g of x equal tangent inverse x. Then my f of x equals tangent x. And here we had to restrict the tangent function to be between negative pi over 2 and pi over 2. And we can't include the pi over 2's because recall that the tangent of pi over 2 is undefined. So it's not or equal to, it's strictly less than's here. And y here goes for all reals. Y goes for all reals. Right? It goes from negative infinity to infinity. And so for the arctangent function, the x's go to all reals. And the y values between negative pi over 2 and pi over 2. We also know that if f of x is tangent x, then f prime of x is secant square x. So then d by dx of tangent inverse x, following the pattern, the rule that we developed on slide 1 of this, we would have 1 over secant square of g of x, arctangent x. Alright, and we then have to think of the drawing for this. Alright, so we need to think of this as our y. Let's think of the tangent inverse of x as our y. And again, we could have two possibilities here. Y could be positive, y could be negative. If y is positive, it's between 0 and pi over 2. All right, so there's y1. And here's my reference triangle. If y is negative, it would be between negative pi over 2 and 0. So here's the other possibility. Here's y2. And there's my reference triangle. All right, so now y is equal to tangent inverse x. That means that tangent y equals x. Tangent of y is equal to x. Tangent is opposite over adjacent. So again, thinking of this x as x over 1. Here we would have an x. And now the adjacent is 1. So this is going to be tough to see, but here's the 1. The 1 is the adjacent side of the triangle. And again, this would be if x was positive. If x was negative, we would have here, x, this would be the negative. And again, the adjacent leg would be 1. Now in either case, if you calculate the hypotenuse of this triangle applying the Pythagorean theorem, in either case, if we find that, we would have the square root of 1 plus x squared. So then we would have that d by dx of arctangent x would be secant square. So we have to find the secant of y and square it. Now recall that the secant is the reciprocal of the cosine. So I'd have 1 over the secant square. And the secant would be the hypotenuse over the adjacent. So that would be the square root of 1 plus x squared over 1 squared. And when we simplify this, that would just be 1 over 1 plus x squared. So d by dx of the arctangent, or tangent inverse x, is equivalent to d by dx of the arctangent function, arctan x, and is 1 over 1 plus x squared. So we've developed the formulas for the arcsine, the arccosine, and the arctangent. Now we can do something similar for the other inverse functions. They aren't used as frequently as the arcsine, the arccosine, and the arctangent, but I'll go ahead and list them here for reference, and you could use a similar technique as I have for these 3 examples to develop these formulas. So d by dx of the cotangent inverse function is negative 1 over 1 plus x squared. D by dx of the secant inverse function is 1 over absolute x times the square root of x squared minus 1. And d by dx of the cosecant inverse function is negative 1 over absolute x square root x squared minus 1. So I hope you saw that there were some patterns there. Right? If we go back to the previous with the arcsine and the arccosine, notice that they had the same basic form, 1 over square root of 1 plus x minus x squared. But for the co-function, there was a negative. Right? Negative 1 over 1 square root of 1 minus x squared. For the arctangent and the arccotangent, again, similar pattern. 1 over 1 plus x squared. And for the co-function, there was a negative. For the arcsecant and arccosecant, again, same pattern. But for the co-function, again, there was a negative. So there's a pattern to these. All right, so now that we've got these these examples, let's actually differentiate some functions. So here I'm asked to differentiate y equals arctangent of 6x squared. So now let's think about this. I have an arctangent function. I just developed that formula, but it's not just arctangent x, it's arctangent of some function of x. So what am I going to need to use here? If you said the chain rule, good job. Alright, so if y equals arctangent of 6x squared, then y prime would be, let's see, the arctangent, that's 1 over 1 plus something square. So I'd have 1 over 1 plus 6x squared square times. Now here's the chain rule. I'd have to differentiate the 6x squared, 12x. So we might write that then as y prime is equal to 12x over 1 plus 36x to the 4th. That's what I would write. Y prime is 12x over 1 plus 36x to the 4th. Alright, why don't you take a few moments, pause the video, and try these other exercises. And here's a hint. If you do this second one, this f of x equals this strange looking expression, if you do that second one correctly, something really nice happens. Alright, so again, this would be a good time to pause. Alright, I hope you paused and tried these on your own. Alright, so we were given f of t is -3 sine inverse of 7t. We need to differentiate this. Alright, so then f prime of t, we carry the -3 along. It's just that's a constant factor. Alright, so now for the sine inverse, that was 1 over the square root of 1 minus something square. 1 over the square root of 1 minus, and it's not something in this case, right? It's not just x. Now it's a 7t. That needs to be squared. And that's multiplied by, from the chain rule, the derivative of the 7t, which is 7. Alright, so I'd clean this up a little bit. F prime of t. Oh, sorry, yeah, not x. I wrote x. It should have been a t there. F prime at t is then, let's see, we'd have a negative. I'll put the negative in front. 21 over the square root of 1 minus 49t squared. Alright, second exercise here. I've got f of x is x times the arctangent of 4x minus 1/8 times the natural log of 16x squared plus 1. Alright, so we have a couple things we have to do here. First, we have f of this first term here has x times tangent inverse of 4x. So here I'm going to have to use a product rule. And then within that product, in calculating the derivative of the arctangent function, I'm going to have to use a chain. For the second term, this minus 1/8 natural log 16x squared plus 1, here I'm going to have to use a chain rule. Alright, so let's calculate a derivative here. F prime at x. First term, I'm going to bracket this. So for the first term, for x times the tangent inverse of 4x, applying the product rule, I'd have 1 times tangent inverse 4x plus x times. Alright, now I need to calculate the derivative of tangent inverse of 4x. So that would be 1 over 1 plus 4x quantity square times 4 from the chain rule. Alright, so that whole thing in brackets, that's the product rule. Minus 1/8 times, now calculating the derivative of a natural log function, that's 1 over u, 1 over the quantity, in this case natural law, the 16x squared plus 1, and then times the derivative of that quantity. So 1 over 16x squared plus 1 times, from the chain rule, the derivative of 16x squared is 32x. Alright, so let's clean this up a little bit. Let's see what we have here. I have 1 times tangent inverse 4x. So that's just tangent inverse of 4x plus. Alright, now let's see what this simplifies as. I have an x times a 1 times a 4. I have a 4x over 1 plus 4x squared. That's 1 plus 16x squared. Minus 1/8 times 1 times 32x. Isn't 1/8 times 32, isn't that equal to 4? So I could write the numerator as 4x over 16x squared plus 1. And now if you look at these two terms, plus 4x over 1 plus 16x squared minus 4x over 16x squared plus 1, those are like terms and they are in fact opposites. They add to 0, and so then f prime of x, the derivative of that function, is simply tangent inverse of 4x. Alright, so I think that's a good place to stop on this video. We've developed some ideas for inverse functions, and we've done some exercises with them. So I'll stop here, and then I'll pick back up with the other subtopic, and that's with the hyperbolic functions. Alright, so I'll see you there.